Okay, so this week's speaker is Alex Rasmussen from University of Utah, and he's going to talk about transverse measures on infinite type laminations. Alex?
Yeah, thank you very much for the invitation. So this is going to be a talk about geodesic laminations. In particular, we're going to look at laminations from kind of a dynamical perspective by studying their transverse measures. We'll show that the set of all transverse measures for a given lamination has a very explicit description, and we'll use this explicit description to describe some exotic new phenomena that laminations on infinite type surfaces have. And this whole talk is going to be joint work with Mladen Bestvina. So the setting is that we have a hyperbolic surface. So X is a complete orientable hyperbolic surface without boundary. So there are quite a few probably very familiar examples. Maybe we have a closed genus 2 surface, or maybe our surface has a cusp. That's certainly allowed. But these two examples are both what we would call finite type surfaces. And finite type just means finite genus with finitely many punctures. But we're not going to restrict ourselves to studying finite type surfaces today. So we'll also look at surfaces like this, for instance. So this is an infinite genus surface with a single end, or maybe a surface like this, which you can obtain by gluing together infinitely many copies of hyperbolic pairs of pants. So this surface actually has genus 0, but it has a space of ends as a topological space, which you can just check is a Cantor set. So the surface here is actually topologically just a sphere minus a Cantor set. So these two examples are both what we would call infinite type. So again, that just means infinite genus or infinitely many punctures, or both. The main objects of study today are going to be geodesic laminations. So a geodesic lamination on X is a closed subset, which is a disjoint union of complete simple geodesics. So I'll give one example of a simple geodesic lamination, and then kind of draw a cartoon picture of more general type of geodesic lamination. And we'll see some further examples later in the talk. So here's a very simple example of a geodesic lamination. So let's take that genus 2 surface. And as an example of a geodesic lamination, we could just take, for instance, two disjoint simple closed geodesics and take their union. So the union is a geodesic lamination. And we'll say that this has two leaves. So a leaf is just the name we give to one of the geodesics making up the geodesic lamination. So there are just two geodesics involved in this lamination. Here's kind of a cartoon picture of a geodesic lamination. So typically, laminations are significantly more complicated than this very simple example here. They'll have like uncountably many leaves, and they're very difficult to actually draw accurately. So I'll just kind of give a little cartoon. So kind of from a distance, you can't really tell so much what's going on. There are many geodesics that are all kind of squished together, very close. So what I want to talk about is what you see when you kind of zoom in on this picture. And typically what you're going to see is like a Cantor set of leaves. So here, when we zoom in, we see kind of two branches coming apart. And on each branch, if we kind of look horizontally across the branch, we'll see just a Cantor set of points. So this is kind of the typical picture. Laminations are very complicated. When you zoom in, you'll see infinitely many leaves kind of coming together and coming apart in complicated ways. All right, so that's just a cartoon. We'll see more examples of geodesic laminations later on. So I'm going to make one more technical assumption on our hyperbolic surface, which is that X is of the first kind. And what this just means is it contains no hyperbolic half planes. So a hyperbolic half plane is basically what you would imagine. You just take the hyperbolic plane and take a half plane inside of it. And you don't want to see a copy of this half plane here isometrically embedded inside of your surface. And the reason we want to assume this is that when the surface is not of the first kind, geodesic laminations can be pretty nasty. They can have interior, they can have splittings in multiple different ways as unions of geodesics. So they're pretty hard to work with. So it's a recent result of Sarich that when the surface is of first kind, any geodesic lamination will be somewhat nice. So X first kind means that any geodesic lamination on X is nowhere dense. So a lamination will be really an inherently one-dimensional object. So we can kind of feel free to not dwell on this assumption too much, but it will just be necessary to make the theorems that I state true. Okay. Now, so we're going to be proving results about transverse measures in this talk. So we have a geodesic lamination lambda on our hyperbolic surface X. A transverse measure mu is a collection of finite Borel measures, which I'll denote mu sub tau. And these Borel measures live on all arcs tau transverse to lambda. Okay, so it's just a collection of measures, but we need a couple other properties. So these measures should be invariant under one, isotopies, and two, passing to subarcs. So you could state these invariance properties in words and equations, but I feel that's not the most enlightening. So instead, I'll draw a picture to explain these properties. So what does it mean for the transverse measure to be invariant under isotopy? So we have two arcs, sigma and tau, which are transverse to lambda, and they're isotopic through some sequence collection of transverse arcs. So this is kind of like the track of the isotopy, and every leaf of lambda that hits sigma is also going to hit tau. Okay, the blue stuff here is lambda. And we want the measures on sigma and tau to be the same in some sense. And the way we quantify that is as follows. So if we follow this isotopy for all time, at time one, we get F, which is a homeomorphism from sigma to tau, respecting the intersection with lambda. And what we want is that the measure on tau is just the push forward of the measure on sigma under F. So this is saying that the measures are the same in some way. And for passing to subarcs, we have kind of a similar picture. So we have maybe a transverse arc sigma, we have a subarc tau. These are both transverse. And here's our lamination running through again. And what we want is that the measure on tau is just the restriction of the measure on sigma. So the measures agree. Okay, so transverse measures are kind of like an analog of invariant measures for dynamical systems. The analogy comes from considering the leaves of the lamination as being similar to flow lines of a dynamical system. And then if you kind of take that perspective and push the definition through, you see that it more or less matches up with the definition of an invariant measure. So let me give you one example of a simple transverse measure. So let's take a very simple geodesic lamination. So lambda can just be a single, simple closed geodesic like this. And what kind of transverse measure can we assign to this? Well, we can assign the counting measure. So the counting measure counts points of intersections with lambda. Okay, so the name kind of makes sense. So maybe we have some transverse arc tau, and our transverse measure will just count the points of intersection. Here there are 3 of them, 1, 2, 3. So, okay, we need to assign a Borel measure to each transverse arc. So what Borel measure will we assign? Well, the Borel measure on tau will just be a sum of Dirac masses on the points of intersection. So in this case, for this particular transversal, it's a sum of 3 delta masses. Okay, so very simple example of a transverse measure. Again, usually they're going to be much more complicated than that. So now we want to be good dynamicists. And as dynamicists, we want to understand not just a single invariant measure, but we want to understand all of the invariant measures for a given dynamical system. So analogously, for a given lamination lambda, we want to consider the set of all transverse measures to lambda. Okay, so far this is just a set, kind of boring, but this has some extra structure. So first of all, this has the structure of a cone. This is not too hard to see. So a cone is just a set in which you have natural operations of addition and scalar multiplication. So for instance, if we have 2 transverse measures to lambda, we want to say how to add them together. And how do we do that? Well, it's not too hard. We just add them transversal by transversal. Okay, so we for any given transversal tau, we just add mu tau and nu tau. That gives us another transverse measure. And we can scale in exactly the same way by non-negative scalars. So the scalar multiple is just obtained analogously. Okay, so this is a cone. It also has some extra structure. So it has a topology, the weak star topology. And this is analogous to the weak star topology on measures. How is that defined? Well, it's defined in terms of integrating functions. So we have maybe a continuous function f defined on some transversal tau, and then we get a function on our cone of transverse measures m of lambda by integrating. So what we do is we just take a transverse measure and we integrate it with respect to f. That gives us some function on our cone. And the weak star topology is the coarsest topology that makes all these functions continuous. So this is the coarsest topology such that for all f continuous defined on a transversal, the function on the cone obtained by integrating is also continuous. Okay, so now we have a question arising from the structure. So what does this cone m of lambda look like? So it's a perfectly good topological cone. What does it look like up to homeomorphism? So to gain some motivation for this question and the answer to this question, I want to first look at the case of laminations on closed surfaces. So these are very well understood. So let's take X to be a closed surface for the moment. And let's take lambda to be some geodesic lamination. What does this cone of transverse measures, m of lambda, look like? Well, it has a very simple structure. It's just the cone on a finite dimensional simplex. So the picture is very simple. You just imagine your cone looks something like this. So maybe it's three-dimensional. And then if you cut and take a little cross section of this cone, you see a little two-dimensional simplex. This is what m of lambda looks like. Of course, the dimension can be higher than this, but it's going to be finite. Another way to think of this cone is just as the positive or non-negative orthant inside of Rn for some value of n. So very simple structure. But we can also say a lot more about geodesic laminations on finite type surfaces. These were very famously studied by Thurston. So he studied also a bigger space. So he studied the space ML of X of all measured laminations on X. So I'm going to kind of highlight the word all here. So we're explicitly not fixing a single geodesic lamination here. We're allowing the lamination to vary, and we're also allowing the transverse measure to vary. He showed that this space has a very simple structure as well. So ML of X is just homeomorphic to a Euclidean space, dimension 6G minus 6, where G is the genus, and it has a natural piecewise linear structure. Okay, great. So these spaces of laminations turn out to be very simple in the closed surface case. But let's back up a little bit. Why do we actually care about studying spaces of laminations? Well, some of the biggest motivations come from mapping class groups and Teichmuller theory. So here's another really famous classic theorem of Thurston. So he studied another related space, PML of X. This is just the quotient of ML, where you mod out by scaling. So it's just a sphere, and this compactifies the Teichmuller space of quasi-conformal deformations of X. So they'll note that by curly T of X. So this is a very important space, and a large part of its importance comes from the fact that the mapping class group of the surface acts on it in a nice way. And the reason this sphere PML is so important is that the action of the mapping class group on this Teichmuller space extends continuously to this sphere PML. So, okay, so T of X turns out just to be a ball topologically. PML, again, is a sphere. So you can very loosely think of this as being analogous to a hyperbolic manifold group acting on hyperbolic n-dimensional space with its boundary sphere. And this closed ball is one of the most important tools for studying mapping class groups. So naturally, we want to extend some of this machinery to understand mapping class groups of infinite type surfaces as well. And in order to do this, we're going to need to understand geodesic laminations a lot better. So let's take X to be infinite type now. And what can we say about geodesic laminations on X? Well, so far, very, very little is known. But here's a recent breakthrough of Bonahone and Sarich that I want to highlight. So PML here, PML is usually what's called the Thurston boundary of Teichmuller space. So we want to produce some kind of analog for the Teichmuller space of an infinite type hyperbolic surface. So Bonahone and Sarich say that there exists a Thurston boundary for the Teichmuller space of X. So this is some kind of boardification of the Teichmuller space, which a natural quasi-conformal mapping class group extends continuously to. Okay, so it's some big new tool that we have for studying mapping class groups of infinite type surfaces. And again, in order to really take advantage of this tool, we'll need to understand spaces of geodesic laminations a lot better. So in particular, what kinds of spaces of geodesic laminations are there? Well, there are a lot. We have these cones of transverse measures, M of lambda. We already introduced these. These are natural important subsets of these spaces ML of X of all the geodesic laminations, measured geodesic laminations on X. And then there are just like tons of different variations like bounded, measured laminations, etc. So it would be good to understand all of these spaces. Today, I'm just going to focus on these cones of transverse measures, M of lambda for a fixed lamination lambda. So we want to describe these cones of transverse measures. And our first theorem will do exactly that. So what do these cones of transverse measures look like? So M of lambda is linearly homeomorphic to an explicit inverse limit of finite dimensional cones. So what does this look like? We have some kind of sequence of cones. We can just think of these as the positive orthant in some Euclidean space. So there's going to be an infinite sequence of these, and these are bonded together by certain linear maps. Okay, and M of lambda is just the inverse limit of this sequence. If you're not extremely familiar with inverse limits, let me define it for you. So the inverse limit is the space of consistent sequences in the product of all these finite dimensional cones. So we take the product of these cones, and then we want to take sequences in the product which one element gets mapped to the next one down under the map pi I. So consistent sequences with respect to this system of maps pi I. All right, so that's the theorem. That's what these cones look like, but there's kind of a weasel word here, explicit. I mean, so far this theorem doesn't actually seem all that explicit. It seems a little mysterious. So let me show you the idea of how you make this theorem much more explicit. So I'm going to make a simplifying assumption, which is that our geodesic lamination has no compact sublaminations. Now, this assumption is not necessary for the theorem. It just makes things easier to describe. So where is this inverse limit going to come from? Well, it comes from studying an exhaustion of our surface. So we're going to choose an exhaustion of our surface like so. So we have some surfaces, x1 contained in x2, contained in x3, etc. And being an exhaustion just means that the union of all of these is equal to x. So this is an exhaustion by finite area surfaces with geodesic boundary. So what does this look like? So let's take this infinite type surface that we saw earlier, infinite genus with a single end. So what does an exhaustion look like? Well, maybe we take our surface x1 to be this genus one piece at the end. Then we can take x2 to be a larger genus 2 piece. And then we just keep going. So our next piece will have genus 3, then genus 4, etc. So we're just eating our surface up by compact subsurfaces. And then let me draw in our geodesic lamination. So something complicated. I don't really understand what's going to go on exactly. Probably it has infinitely many leaves. They interact in some kind of complicated way, whatever. But what we want to do is we want to kind of ignore most of the surface and just study the intersection of the lamination with one of these pieces in our exhaustion. So maybe we take this genus 2 piece and just study the intersection of the lamination with this genus 2 piece. And what we see is that the intersection of lambda with xi is just a bunch of arcs. Most likely there are going to be infinitely many of them. And even though there are infinitely many of them, there are going to be only finitely many up to homotopy. So this intersection has finitely many homotopy classes of arcs. So that already goes a long way towards explaining our inverse limit. The number of homotopy classes of arcs on xi is just the dimension of our ith cone in this inverse limit. Okay, so we've basically explained the finite dimensional cones coming up in this inverse system. They're just cones of the dimension equal to the number of homotopy classes on the surface xi. Let's give a shorthand name to these cones. So I'll call the ith cone Ci. So I've explained what the cones in this inverse system are. I still need to explain the maps between them. And again, to do this, I'm going to just draw a picture, which I think is the most enlightening way of doing it. So let's study maybe the first two surfaces in our exhaustion, x1 and x2. Maybe they look like this. So let's just assume they're planar surfaces. So x1 has 4 boundary components and x2 has some more. So let's just say that x1 has 2 homotopy classes of arcs of intersection with the lamination. Again, there could be infinitely many showing up here. But let's just say there are 2 up to homotopy. And then we want to move from x1 to x2. So this smaller surface is x1, the larger is x2. And what we notice is that when we move to x2, all of the arcs on x2 are going to intersect x1 in some way. And every time they intersect x1, they're going to intersect it in some arc homotopic to one of the arcs on x1. So let's say that x3 has 3 homotopy classes of arcs, 1, 2, 3. Let me add in some boundary components to make everything essential. And so we know now that for our surface x1, there are 2 homotopy classes. So our first cone has dimension 2. X2 has 3 homotopy classes. So our second cone will have dimension 3. And now we want to write down our matrix pi 1 from C2 to C1. And what this is going to do is it's just going to count the number of arcs of intersection of each arc on x2 with x1, which are homotopic to each homotopy class on x1. So in this case, our first red homotopy class runs over the blue homotopy class 1 once and the blue homotopy class 2 once. So our first column is going to be 1, 1. Our second red homotopy class doesn't run over the blue homotopy class 1, but it does run over the blue homotopy class 2 twice. So our second column is 0, 2. And our third red arc is disjoint from x1, doesn't run over any homotopy class on x1. So we'll just put a 0, 0 as our last column. And that's the idea. So in words, pi I just records the number of times that the homotopy classes on xi plus 1 traverse those on xi. So now we can state a really explicit version of our theorem. So here's the explicit version. So the cone of transverse measures M of lambda is linearly homeomorphic to the inverse limit of these cones Ci together with these linear maps pi I. Okay. So again, this theorem works if there are compact sublaminations. You just need to work a little bit harder to state what the maps are. So let's run through one example just to make sure that this theorem actually works. So I'm going to draw a pretty simple geodesic lamination. It's just going to have leaves like this. And I'll take the same exhaustion that we had before. Now you might be able to guess what the cone of transverse measures is without doing any computation at all. So you can think about that if you like. but I want to run through the computation just to make sure the theorem works. So on our first surface, x1, we just have a single arc of intersection. On x2, we have two arcs like those. On x3, we have three arcs, etc. So you see the pattern. So our cones are going to look like this. And now we just need to work out the maps between these cones. So when we go from x2 to x1, we see, well, the first homotopy class on x2 is this. It runs over the first homotopy class on x1, but the second homotopy class doesn't run over any homotopy class on x1. So our first matrix is 1, 0. Then from x3 to x2, our first homotopy class runs over the first homotopy class on x2. Our second runs over the second. And our third is disjoint. So our second matrix looks like this. And you see the pattern that starts to develop. We have just identity matrices with a column of zeros tacked onto the end. So what does something in this inverse limit look like? So we have vectors in each cone, and these vectors just need to map to each other under the linear transformations, which just forget the last coordinate. So that means these x's need to match up, these y's need to match up, etc. So what happens is that at each stage, you just get a new coordinate, and there are no relationships between the coordinates at all. So we can describe the cone of transverse measures in this case as just being an infinite product cone, like so. So just an infinite product of rays r plus. And that kind of makes sense. So this cone is basically just recording a number associated to each leaf in the lamination, of which there are countably many. Okay, so for the remaining part of the talk, I want to focus on some kind of exotic behaviors of laminations on infinite type surfaces. So first, we have the following exotic property, which follows from this description that I gave. So if X is infinite type, then there exists a lamination lambda on X such that its cone of transverse measures is equal to 0. So there are no non-zero transverse measures whatsoever. So this is definitely an exotic property compared to laminations on finite type surfaces, which always do admit non-zero transverse measures. And then for the last couple of theorems, I'm going to work on building up a better picture of kind of the shape of these cones of transverse measures. And we're going to study them using their bases. So a base is basically the natural notion of a cross-section for a cone. So it's a compact convex set such that 0 doesn't lie in B, and for all vectors in C other than 0, there's some unique scalar multiple which lies inside of B. Okay, so again, this is just the natural notion of a cross-section for a cone. And the picture is like the same picture we drew earlier, where we had this three-dimensional cone, and we take a cross-section. So this is just some compact convex set intersecting every ray exactly once. So that simplex there is going to be a base for the cone. Now, the reason we want to study bases is that they give us a better idea of the shape of the cone. The cone is really like a ray times the base. So we can get an idea of the shape of the cone by just looking at the base. And the base is a compact convex set, so we can do a bit better trying to visualize it, and we have more tools to deal with it. The problem is there's no reason to expect that a base actually exists. So in fact, there may not be a base, but in our third theorem, we show that there does exist a base as long as the lamination is sufficiently nice. So if there exists a compact subsurface of X intersecting every leaf of lambda, then this cone of transverse measures, m of lambda, has a base which is a nice type of space, namely a show K simplex. Okay, so I'm not going to give the full definition of a show K simplex here, but it's basically the natural infinite dimensional analog of a simplex. The defining feature is that every point of the simplex is the barycenter of a unique probability measure on the space of extreme points. Right, this definition might not be that intuitive if you haven't done any functional analysis in a while, but the idea is that this is generalizing the property of a finite dimensional simplex in which every point is a unique convex combination of the vertices. So the extreme points are like the vertices of the simplex, and this property of being a barycenter of a probability measure is like being a convex combination of the extreme points in some ways. So an example of a show K simplex would just be a finite dimensional simplex. So maybe we take this simplex with vertices u, v, and w. Those are the extreme points. And if we take any point inside this simplex, say the midpoint, we can write it as a convex combination in a unique way. So in this particular case, V, the midpoint, is just the average of these three vertices. Okay, so now we have a converse question. So we know that our cone can admit a base, which is a show K simplex. So what kind of show K simplices can appear as bases? This will give us an idea of what kind of shape our cones of transverse measures can have. So let me give you one quick example, which is slightly more exotic. I'll draw fairly simple geodesic lamination on this same infinite genus surface. So it will have leaves which just kind of wrap around more and more of the handles in this picture. And in the limit, there's a single leaf which just kind of wraps around all of the handles. Now, here's our geodesic lamination lambda. We could do a calculation to figure out a base. I just don't want to spend the time doing that at the moment. So in this case, I'll just say the base is infinite dimensional, and you can find a base which is very explicit describe its extreme points in a very explicit way. So the extreme points are just identified with delta masses on the different leaves of this lamination. So there are infinitely many, countably many leaves, exactly one of which, this one on the bottom, is a limit of the other leaves. And okay, so these delta masses on each leaf are just the extreme points of the space. So in this case, you can see that the delta masses on this sequence will converge to the delta mass on the limiting leaf. So our set of extreme points has some non-trivial topology. It's just an infinite convergence sequence. So we have an infinite sequence converging to a single point. You can identify this with omega plus 1 if you like ordinal numbers. So this is just some kind of infinite dimensional sequence, simplex with a non-trivial topology on its vertices. But generally, showcase simplices can get much, much wilder. An example is the Poisson simplex. This is a simplex in which the extreme points are dense. So this is a really, really wild space. So this is a simplex, and remember, extreme points are like vertices, so every point, including interior points, is somehow like a limit of vertices. Really, really wild. So we want to know, are there any restrictions on the shapes of our cones on the showcase simplices that can appear as bases, or are there not? Can they be arbitrarily wild? So I'm going to state one more definition and then just give you the answer to this question. So our lamination lambda is minimal if every leaf of lambda is dense in lambda. So minimal laminations are very complicated. In particular, basically none of the laminations we've drawn in this talk have been minimal. And our final theorem will answer this question that I asked about the shapes of these cones. So if delta is any compact metrizable showcase simplex and X is infinite type, then there exists a minimal lamination lambda on X such that M of lambda, this kind of transverse measures, has delta as a base. So the answer to our question is there are basically no restrictions whatsoever. Every showcase simplex can show up on every infinite type surface of the first kind, and you can even allow the lamination realizing it to be minimal. Okay, so that's going to be it. Thank you very much.
Okay, thank you very much, Alex, for a great talk. Are there any questions for Alex?